Welcome. I don't know what number this is, but it's it's good. So this is the the Distinguished Lecture Series in Causal Discovery, and it's sponsored by the Center for Causal Discovery, which is an NIH Big Data to Knowledge Center of Excellence that formally began in September of 2014. And the major aims of the center include developing and disseminating algorithms, systems that assist biomedical scientists in discovering causal knowledge from very large biomedical data sets. Another key aim is to train up-and-coming scientists and existing scientists to apply these methods effectively. And the center is sponsoring this lecture series in order to recognize distinguished leaders in the field of causal discovery and to provide a forum for them to let us know about some of the cutting-edge developments in the field. Which leads me to our current distinguished leader in the field, Dave Jensen. So Dr. David Jensen is professor of computer science at the University of Massachusetts Amherst, and his research focuses on methods to learn accurate causal models of large social, technological, and computational systems. He's done really interesting work in relational databases and how that actually can be analyzed with causal methods of the sort that we know and love. He's also played a lead programming role on several key conferences, including the ACM SIG KDD Conference on Knowledge Discovery and Data Mining, the IEEE Conference on Data Mining, the International Conference on Machine Learning, and the Conference on Uncertainty and Artificial Intelligence. He served on the board of directors of the ACM Special Interest Group on Knowledge Discovery and Data Mining, the Defense Science Study Group, and DARPA's Information Science and Technology Group, which I believe I actually visited at one point. In 2011, he received the Outstanding Teacher Award from the UMass Amherst College of Natural Sciences, and in 2017, just last year, one of his papers received the IEEE Infocom Test of Time Paper Award. He's also a great guy. So, please welcome Dave.
Thank you very much, Richard, and thank you all for being here. Guess I will go to the official-looking slide of the title of today's talk. I guess because of the need for the mic, I'm going to stand here. I will probably start pacing at some point. You'll have to flag me down and say no. The microphone, I guess, this is important for recording purposes. So what I'm going to talk about today is less about the specific technical work that I've been doing over the last 10 years or so in causality, and more about how I think as a community we should be evaluating the work that we're doing and demonstrating that work to people outside of our technical community. And this is partially based on a paper that we gave at the KDD workshop on causality a couple of years ago, and that a lot of that paper was done by Dan Garant, one of my PhD students, and now we're working on update and sort of re-engineering, rethinking of that paper, and that's work with Amanda Gensel and Dan, who's now graduated, and that'll be coming out sometime in the next 6 months or so. So I want to talk about specifically this idea of evaluation, how we evaluate our research and how well the models that we construct with causal discovery methods work. And I'm going to be intentionally provocative, okay, hoping that I will get strong arguments from all of you saying, no, you're totally wrong. So I'm going to be intentionally provocative here. But here's the...
You can say that anyway, you don't.
No, I'm delighted. I know that's true of you, Richard. I just wanted to be sure everyone else felt free to, to do that. So here's the idea. I tended to call it the big idea, but it's at least the idea, which is that our understanding of causal inference itself and the impact of practical techniques that we develop for causal modeling would substantially improve if we more regularly conducted empirical evaluation of the practical techniques that we develop. And I'll talk more about what I mean by empirical evaluation, but that's the idea. We should be doing more empirical evaluation. Not less of other things, but more empirical evaluation. We should be applying a broader and more consistent set of methods to evaluate the performance of techniques for causal modeling, and those should continue to include theoretical analysis, simulation, but more empirical evaluation. And that in contrast to theoretical work and work in simulation, the use of empirical methods is conspicuously absent from a lot of the current work that we do, my own work included, okay? And that we need to further develop and adopt those methods, and that this would offer an opportunity for us to improve both the quality of our own research internally and a way to increase its external impact so that other communities realize the good work that we're doing and make use of it. All right, so I'm going to first just start out and give you an example of what I mean. Some work that we did for the paper I mentioned and that we're continuing to work with. Then I'll talk about specifically what's hard about evaluating techniques for causal modeling, review what I see as kind of the dominant approach that we've all taken, again, me included, some limitations of that, some alternative approaches, and then what I will jokingly call interventions and potential outcomes. That is, what should we do and what might we expect if we do those things? So here's the example. So a couple of years ago, I said, I'm not entirely convinced by our own evaluations in our own papers, and I'm not entirely convinced by evaluations that I'm seeing in other papers on causal modeling, because I'm not sure that they would actually work in real cases. And I was also being challenged by people who would say, yeah, your work's really interesting, but can you really infer causality? They would say, and I would say, well, absolutely. We've got all these, these theoretical results, and we've got these results in simulation. And they would say, well, but does it really work? And so I said, okay, how do we really go about that? And here's the list of things that I came up with about what we needed. First of all, it needed it to be really empirical. That is, it's a real world system out there that I didn't create. I, as a researcher, or some other researcher in causal inference, causal modeling. Secondly, it needed to have stochastic behavior. It needed to have some element of randomness in it so that we are actually learning probabilistic models. It needed to be identifiable in the sense that we had to be able to determine what was actually the case in terms of causality in that system. It needed to be recoverable in the sense that we need to be able to run it many times under the same conditions. And so ideally, we'd like to have what's sometimes called complete state recovery. That is, we'd like to be able to reset the system back to something else, like a human being is not recoverable in the sense that once you do something to them, they may be permanently changed by that thing, that drug, that training, exercise, whatever. I wanted it to be efficient so we could run a lot of experiments. And I wanted it to be reproducible so that if we did the work, other people at other institutions could also do that same work. Now, this is a big list and a scary list. And I was, said, actually, I think I've got something that matches this. And that is to take large-scale software systems. I'm a computer scientist, so it's not surprisingly that I might think of this. Large-scale software systems that are so complicated, frankly, that no one understands how they work. You talk to anybody in databases, and they will tell you that configuring a database in practice is a black art. Okay, when I'm in really, I'm talking to people outside of causality in computer science audiences, I will say, how many of you have configured a database? And about half the audience will raise their hand, and I'm sure a lot of you could raise your hands. And then I say, okay, and that was easy, right? It was simple, and you were totally confident that you had the right settings of all the little flags you could set, and everybody laughs, because no, there's no way you're confident. You don't really know. In fact, even database experts don't know how to do this really well. There's a lot of trial and error. So what we did was to take a well-known database server, Postgres. Okay, it has been developed over decades. It's literally something like 30 years old. Been developed by thousands of people have contributed code to this, and no one person really understands how it works. Then we took And they have whole chapters in the documentation about how to configure the database. There are a lot of parameters you can set that make it run faster or slower under certain conditions. So then we took a real set of data, large set of data from Stack Overflow. For those of you who are familiar with Stack Overflow, it's a big question and answer site. It's totally amazing. And they make all their data publicly available with a very small number of exceptions about votes. Voting behavior is not entirely public, but about everything else is. And then we took a single instance of the installation, installed it on a particular machine, put all the data on it, and then said, okay, we're going to configure this in many different ways and run trials about how efficiently this database instance can process queries. And so we asked questions sensibly about sort of the efficiency of the performance of the database under various configuration parameters. And you might imagine wanting to do this because you're, in fact, the database administrator and you want to do this. And also, by the way, we had more than 11,000 queries that we didn't write, that were actually run against the web version of that database. So we didn't write the database server software, we didn't write the data, and we didn't write the queries. And so we really have a closed system that we can do massive numbers of experiments on. So that's what we did. We specified a set of treatments. These are things like a flag that indicates how to handle indexing, whether certain fields are indexed, what the particular page cost we associate with random access memory, and the memory level. Do we have a lot or a small amount of memory? And we made these each binary to make things really easy. Okay, so we have binary treatments. We have a set of outcomes, things like runtime, how much reading from disk, how many cache hits, how many times did you try to access something in memory and actually have it be in memory, not have to go to disk to get it. And then there's a bunch of other variables that we might think of as just covariates, okay, other things that matter, like what was the query and what are characteristics of the query. And we even had characteristics of users. Turns out we know something about the people who submitted the queries. So we know something about how many queries they've written before, and what time period was it created in. So we had binary treatments. We discretized all the other variables to try to level the playing field for different methods. Okay, so density-based binning for these different the covariates and the outcomes, and then we said, okay, let's see how various methods work. So the process was interesting. What we did was we said, we've run an exhaustive set of experiments under every possible treatment configuration. We ran every query 5 times or 10 times, I can't remember which it was. And we have all of these results, and we were very careful to clear caches and do everything between each of those queries. And then we sampled the perfect experimental data non-randomly in order to approximate what observational data would look like. So that non-random sampling is very important. In theory, we could actually come up with observational data from database administrators if we went to them and said, how would you configure the database if you were going to run this query? We haven't done that, but we could, and that's actually a next step in this work. But what we did was to do these non-random samples of the perfect experimental data to create the moral equivalent of observational data, where there are, in fact, confounders that we might be able to account for. And then we handed that off to some causal modeling algorithm, learn a causal model, and then we estimate the effects of interventions from the model, and then we see how those interventions actually affected key outcome variables in the data. Okay, we can go back to the original data and get the right answer. We could also rerun that if we wanted to, but that's what we actually have all the data available. Greg.
Maybe I'll just get this, but I just want to make sure, since I understand the observational data, how are you turning the interventional data into observational data by your sampling? And how do you guarantee that it has the properties that you want for observational data, including potential confounding?
I will get there in just a minute. I will get there. It's a very good question, and we did it a particular way, and there's lots of different ways you can do it. And my argument here is not that we did it necessarily the right way. We've made the data available to anyone who wants it, so you can go in and sample it however you'd like to sample it. But I'll give you one example of what we did. Yep. Other questions? Yeah, feel free to interrupt if you've got questions. Okay. So here's our variables. We can group them into categories. Okay, so in the bottom left are the user variables, the year created, when was the query created, and the total number of, when was the account created, not the query, the account created, and total number of queries by that user. So sort of in a sense of experience. Some characteristics of the query itself, upper left, upper right, the database configuration, and lower right, the variables corresponding to the processing of that query. These are our treatment variables, okay? And these are the outcome variables we're going to focus on, the results I'll present. And what we did was to take retrieved row count, which is something in theory that you would be able to know, once you have a query, it has a logical relationship given the database to how many rows that query actually corresponds to. That's what a database is intended to do, is actually retrieve those rows. And so we had a count on that, and we used that variable to bias the settings of these three configuration variables. So in terms of how we got the observational data and made the pseudo-observational data, what we did is we took this variable and used it to bias which treatment configurations we are likely to see in the data. And thus, it's not surprising you actually see these three edges in the model that we've learned. This is the model learned by GES. Okay, and only one of them gets oriented. But this is the Markov equivalence class we get out of GES. And in the paper, it gives you the details of how we actually did that, and we varied it over, very strong or fairly weak. Actually, what I'm showing you is a moderately weak configuration where we didn't actually bias things that much. So this is the graphical model that's learned, or the graphical model family that's learned, because as you can tell, some of these edges are not oriented. And it's pretty complicated. You look at it and you go, wow, not really sure that this is learning much. I want to do something, which is I want to show you now how strong those edges are. We've grouped them into three categories and just use line weight to indicate how strong the dependence is. And now I'm going to drop just the lowest third of those edges. Okay. Now we see something actually very interesting when we're looking at the strong edges. First of all, user variables only influence query variables, or only causal for query variables. That makes sense. Users affect queries, but conditioned on those queries, they don't really affect anything else about processing. If you look at query variables, they are causal for only processing variables, which again makes sense. They don't actually affect the user. Okay, they affect how that query gets processed, and the configuration variables up here only affect processing, they don't affect how someone writes a query. So this, at a high level kind of structural sense, level, this graph makes sense. And it corresponds to what we know about, mostly what we know about how database servers work. While we tend to be very interested in how different methods work, and I'll mention some results later about that, the thing that most people outside of the causal discovery community care about is they say very frequently, the first response is, well, why don't I just use machine learning to do this? Why don't I just use an associational model? What's wrong with that? And so one of the first things I wanted to do was actually compare that. So what we did was to compare a state-of-the-art associational model, a random forest, to a causal graphical model constructed using GES. That's the model I just showed you. And what we're going to do is we're going to say, we're going to give all of the query variables, user variables, and configuration variables to everything except the one variable we're trying to predict to a random forest. We're going to say, we actually give it that as well. We say this is the target variable. Predict the outcome variable given all of the other variables. So we build a conditional model. And then we compare it to ground truth. And ground truth we have, of course, when we intervene on those configuration variables, here is the ground truth. And when we intervene on those variables, and the associational model doesn't really have a notion of intervention, but when we intervene, when we set in the associational model the variables, the configuration variables to a particular value, here is the distribution that's predicted for this outcome variable cache hits. And by the way, there's only two values that ever come out with this particular setting of the configuration variables, so that's why we only see two possible discrete values. And you say, well, that's not bad. The associational model did all right. That's what GES says when we intervene. And we actually use the do calculus, okay, and say we're going to intervene on those configuration variables. And this is the model. This is the prediction we get out, and we should be very happy, okay. Here's what the associational model says for disk reads. And it's not so rosy for the associational model. This is a pretty bad distribution, okay, compared to the ground truth. And there's what GES says. And this is more or less what we would expect, but it's nice to see this in practice. And here it is for runtime, not so good for the associational model, much better for GES. In fact, very much better for GES. When I presented these as part of a tutorial that I've been doing for the last several years for our social scientists at UMass, I had a fairly prominent political scientist in the audience who didn't know much about graphical models, and I showed him these, and he looked at me, and apologies for the language, he said, "You're shitting me," he said. And I said, "No, I'm not. This is really, really what happens." And this has been a big surprise to lots of people outside of the causality community, that they just don't expect that these graphical models are actually going to work. Now, it should be noted that this is a very clean set of data. We have essentially no measurement error. Some of my systems colleagues would disagree with me, but essentially no measurement error. We have almost perfectly enforced the IID assumption. Okay, each run is absolutely independent of the others. Okay, conditioned on the setup. So IID is absolutely valid here, or exchangeability is absolutely valid. And so we've got a lot of things that we like. I cannot guarantee you that we have no confounding, no latent confounding, because there is probably a lot of variables here that I haven't accounted for and that we haven't measured. But this is what we get in this case. So some conclusions. The first is that this is a very nice existence proof that it is possible to learn a reasonably accurate causal model for at least this particular case and these particular interventions and outcomes. Certainly, Peter. Not really. So over time, if an average user would, so the question was about feedback, by the way, for those who didn't hear. Over time, a user might revise their query or something like this. But in this case, it's a one-shot thing. And we specifically searched the space of large-scale software systems, looking for software systems that had this one-shot property. That we didn't want feedback because we wanted to test relatively straightforward algorithms like GES, PC, etc. So we had to work pretty hard, actually, to find no feedback. If you look at, for instance, an operating system, it's got huge amounts of feedback. And so we didn't do that. If you look at networking systems, a huge amount of things. By the way, we did find two other instances that had this same property. One is essentially a compiler, a Java development kit. Okay. Again, you submit a program, it runs through, it compiles it, it has output, and it ends. And then we reset everything, we do it again. And we did HTTP processing, that is web processing, where we request a page, it goes out, does a bunch of stuff, comes back, done. And we can control things about the nature of that request and the browser that the server thinks it is sending a page back to. And again, it has that kind of one-shot property. That was intentional, and it is not realistic in many cases. Second thing is we can, for our sort of interest, we can compare performance of different algorithms. And in this particular case, GES appears to outperform, say, PC and MMHC, both in terms of the how well it matches the distribution. Here, lower is better. This is total variation. This is how far do the inferred interventional distributions differ from the actual distributions. So lower is better, and GES does pretty well and has extremely low variance, which was a bit of a surprise. And MMHC and PC, on this case at least, don't seem to do as well. And there are some practical sort of things that we got out of this. First of all, it's very clear to us that not all structure errors are created equal. We kind of knew this to begin with, but we have some very vivid demonstrations of it here. And that in many cases, we can make grievous errors in the structure, and it's completely unimportant to the particular pairs of treatments and outcomes that we care about. And sometimes we make errors. You saw that the edges to take into account confounding were in fact unoriented. And even if we'd made errors in those, it doesn't much matter because we're intervening on those those configuration variables. And so when we intervene on those, we remove those edges, and it doesn't affect inference. It does affect how we learn those probability distributions. But in any event, there's a lot of sort of things ideas that this spurred in our thinking. I will also point out, just as a technical note, that what we did, given that we learned a Markov equivalence class and not a fully specified model, what we did was to parameterize every instance of the model in that Markov equivalence class and average over the results. Straight averaging. No likelihood weighting or anything else. And when there were too many to do that, we would sample 100 randomly, and we would average over those. We were surprised that even in that situation, it ended up doing pretty well. Okay, so questions about that example?
Just a naive question. When you reset this and ran it every time, is it running in isolation on the processor? In other words, were there other processes that were going and maybe occupying the cache in a sort of pseudo-random way?
Certainly, there were operating system processes that were running. Okay, but we were not running anything else on that machine. It wasn't like it was a departmental server or something. It was a locked down machine that we tried to minimize the amount of other stuff that's going on. Doesn't mean that there's still, as I said, my systems colleagues will tell me there's a lot of other stuff that happens, and we did see a little bit of variability in those results.
It seems that some of the parameters of the database that you might be looking at varying are exactly designed to account for situations other than
multi-user
those you're using. Well,
right.
Well, like clearing the cache, that some of the indices
Sure.
and the caching things are designed for repeated queries and sequences of operations rather than one hits.
Absolutely, and we are not trying to tell database people how to do their job.
Okay,
Yeah,
great.
we may get to that because I think there's some interesting opportunities there, but yeah, that wasn't our interest here. Yeah. Joe.
You say all errors are not created equal. You compare GES to PC, and PC is a lot worse. Does that mean that errors were a lot worse? Why PC stable instead?
So great question. No, we didn't, and yes, that would be a great thing to do. And my suspicion and my recollection, this is now 2 years ago, my recollection is that we were seeing more edge orientation errors because this was vanilla PC. So yeah, absolutely. And data's available, data sets are there, and for all three cases, I'd recommend if you are interested, start with Postgres because it's, I think, the most interesting underlying system in terms of how many, how rich the causal dependencies are. We're going to be doing some additional work on the other two to try to figure out, what's going on because we kind of did some initial experiments and then largely left them alone. But yeah. So it will come as no surprise for me to tell you that predictive accuracy is not a very good way of evaluating causal modeling, and that's part of the challenge of doing it. We've got data. If you're a standard person coming out of machine learning, you're going to say, oh, we need a training set and a test set. We just need to divide up our training set our data set into training and test, and then we can figure out, how well the model works. No, that doesn't work in causal modeling because, of course, you want to infer whether the model does a good job of inferring the effects of intervention, and the observational distribution doesn't do that for us. So what we need to do is come up with alternative methods, and that's what we've done as a community. But I will also tell you that, we're for people outside of the community, we're sort of fighting a kind of whole set of traditions that have been developed over a long period of time and driven into practice, and expectations of how evaluation works in machine learning and statistics and the fields that have contributed to causality. But I also think, importantly, there are some kind of sociological and cultural barriers, and that's what I've just mentioned, and we'll talk a little bit more about it. First thing is that I think there are many diverse communities that have contributed to methods in causal inference and modeling from observational data. So computer science, statistics, philosophy have all contributed strongly to causal graphical models. Work in statistics, social science, econometrics have contributed to the potential outcome framework and various methods that are generally sort of grouped under that kind of that framework. And work in physics and computer science have recently, developed these distributional methods. I'll just group a lot of work under this general category of distributional methods, where you're just looking at pairs of variables and saying, based on their distributions, are those causal? And each of these communities, the individual communities I list on the left-hand sides there, have different task definitions in some cases, different standards for what proof looks like, what evidence looks like, and different traditions of how to evaluate things. I'll talk a little bit about those. So let me give you an example from the community I know best, which is machine learning. So traditional work in machine learning makes evaluation look kind of easy. And frankly, machine learning has been hugely successful because we developed an set of evaluation methods really early that work pretty well, and it's also a pretty easy problem here because we can just take a data set, a real data set, and split it up into training and test, or more reasonably do things like cross-validation. So the first thing is, I guess I should just go with my slides. The first thing is that there are some very well agreed on and long-studied tasks that have turned out to be super widely applicable. So we define conditional probability estimation, and we say, that's what we want to do, and we have a whole bunch of methods to do it, and it's very, very useful to do in lots of different domains, and we've tweaked it in all sorts of ways to be able to be relevant to those domains. We have some very well-established methods for evaluation, including cross-validation, ROC analysis, and other things, and we have a lot of resources available for that evaluation. Big data set repositories, large software infrastructures, for running various kinds of evaluation. And there are lots of other examples within computer science, actually, where it's not quite so simple. Information retrieval, it turns out, is very hard to evaluate unless you've done a lot of work developing data sets. And the TREC competition generated these massive repositories with relevance judgments for various queries that have led to real success in information retrieval. In robotics, evaluation was a very hard thing, and one of the techniques that people came up with was RoboCup, this competitive soccer tournament among robots, which really turns out the community worked really hard to figure out some domain which was intriguing and competitive and would still test a lot of things you care about in robotics. And it's got all sorts of flaws, but it's also got some real successes associated with it. In reinforcement learning, one of the big things that everybody talks about is the backgammon, the reinforcement learning system that learned to play backgammon, called TD Gammon. And it's frequently pointed to as this is proof that reinforcement learning works because this system was able to autonomously learn how to be a world-class backgammon player. And recently with deep learning or deep reinforcement learning, the idea that you could use a deep learning system and learn to play Atari games, the Atari 2600 simulator, to learn to play Atari games at superhuman levels was very impressive to a big swath of people, both inside and outside of the community. And people said, well, gosh, deep learning must really work if you can learn to play Atari games at superhuman levels. I have lots to talk about with that, but we won't go into it. If you're interested, I'm happy to talk offline. So that makes me ask a set of questions about causality. Sorry, what was that?
Casual democracy.
Oh, did I? Oh, God, I can't believe it. I can't believe it. Oh, for me too. No, believe me. Thank you. I love real time. Did you see it anywhere else? I hope not.
No, but we want to have a company.
Casual modeling?
Actually, registered.
Casual research.
It was registered incorrectly. Casual.
Well,
This is your company?
Yes.
I will note.
It's still that
Casual
name,
modeling
right?
problem.
It's still that name. You haven't changed it.
We dissolved it.
Oh, my.
You were too high stress.
So what is our task? So I would state it as my preferred statement would be something like, given an arbitrary intervention X, and I have bold X here because it could be a set of variables that I intervene on, in a system of interest, estimate the effect on some set of outcomes Y. Okay? So I don't, and I'm not going to pre-specify what those interventions are. I may give you a distribution over them or something, but I don't want to just have one particular intervention that you're interested in. But I will point out there's a lot of other possible formulations. So one of them, let's say the sort of limited view of the potential outcome framework, is that given an intervention on a single binary treatment X, estimate the effect on a single continuous outcome Y. Yes, I know there's lots of work that expands beyond this, but this is where most of the work focuses and where it's kind of usually explained out of. Reinforcement learning has a very interesting connection to causal modeling, and they ask the question, given an action policy pi, okay, estimate the long-term discounted reward of taking a particular action and then following a particular policy afterwards. One formulation of reinforcement learning. And it's a continuous action space where you're, not continuous action. It's a action space where you're taking many, many actions over time and trying to maximize your long-term discounted reward. And there are certainly segments of the causality community that would say, really, I just want to answer the question, does X cause Y? That's all I'm interested in. And so, just tell me the answer to that question. Now, I'm going to critique that last one particularly because I think it is a very poorly specified task. In the sense that an answer like yes for a specific variable pair doesn't specify the magnitude of that effect or the conditions under which that effect occurs. And given that, essentially, any answer could be justified by some set of data. Because I'm not specifying any kind of effect size threshold or sample size. And those are the things that you need to do a statistical power calculation to sort of say, what's the likelihood of error? And as someone who's for whom power analysis was driven into me, when I see the answer, yes, this is causal, I go crazy. Or if someone says, no, this is not causal, I go crazy. Because I say, really, I want to know about size of effect that you're assuming, and I want to know about sample size and lots of other things. And also, I want to know the marginal distribution of other potential causes of Y so that I know the conditions under which causality happens or doesn't happen, causal effect happens or doesn't happen. And this is not surprising for me coming out of a causal graphical models community. I care about lots of other things besides just whether that edge is there. I care about the conditions under which that edge might be important and might change our sense of causal effect. So I think we at least have to have strength of effect and some sense of a conditioning set under which those conditions occur. Yep.
So under those issues that you list, do you ever consider dynamics? So like how long you wait for a system to settle down?
Absolutely. Once you get into anything with feedback, wow, things get even more complicated. And I would argue that that's even more why we care or should care about empirical evaluation. That once we get into systems with dynamics, that we really have a lot of questions about what real systems happen out there and what might be a reasonable model of systems that have dynamics. And so I'm going to make some arguments soon about why I think why empirical evaluation is going to give us better answers. So the current.
Sorry, David, I have a question.
Certainly. Who is that? Is that somebody in?
Oh, yeah, this is Quinn. So according to your suggestion, basically we shouldn't use precision or recall at all, right, for performance evaluation?
Yes.
Okay. I just want to make sure I understand you correctly. Thank you.
I'm sorry. Can you say this question again?
So basically, according to what you said, then we shouldn't use precision or recall for performance evaluation at all, right? Because those performance measures just care about whether we have direct edges between random variables.
So I'm going to say that and I'm going to get to this just right the next few slides about precision and recall being strictly structural measures rather than distributional measures. And so if you're just looking at whether edges are there and if they're correctly oriented, I think you can be missing a lot.
Mm-hmm.
Is that?
Thank you.
Okay. So current evaluation methods, there are multiple methods for doing it, and some of them are theoretical. That's great. We prove theorems, soundness and completeness theorems. I've done it myself. It's a very good thing to be doing. And there are some innovative forms of empirical evidence that I'll talk about in a few minutes. But the big point is, at least for work on causal graphical models, one method of evaluation is dominant, and that is assessing the structural accuracy of models learned from synthetic data. And there's some very good reasons we've done this, and it's a good place to start, but it shouldn't be where we end. Because structural accuracy on synthetic data, it basically looks like this. I've got a technique T that constructs a DAG from observational data, and I've got a fully specified causal graphical model M star here that is both a DAG and a set of CPDs. And what I'm going to do is I'm going to generate data from M star, generate a sample S. I'm going to learn a model from S that generates a DAG D sub T, and then I'm going to compare D sub T and D star using some distance function. And that's basically it. The distance function is our sense of how well that technique T is doing. And generally what we do is we of course look at the 2x2 matrix, okay, and we say, oh, there are true positives and true negatives, that's great. Cases where there should be an edge and there is, or there shouldn't be an edge and there isn't, but there's also false positives and false negative errors, and there are edge orientation errors. And so we have a variety of measures that we use: false positive rate, false negative rate. We talk about edge orientation errors specifically. We can do precision and recall. We can do orient precision and recall. And then there are summary measures that include structural Hamming distance, okay, where we'll just look either at the undirected skeleton or at the directed edges. And then there's even some measures like structural intervention distance, and I'll talk about both of those now. So structural Hamming distance is you take a network, and for instance, if this is the learned network down on the lower left, well, we're missing an edge there, so it would have a structural Hamming distance of 1 from the true graph. If you add some extra edges, okay, that's also going to give you a structural Hamming distance of 1 if there's one extra edge. And if you miss an orientation, sometimes you score it with 0.5. Okay, so this might be what we do here for structural Hamming distance. Structural intervention distance says, there's actually a problem with this, that the misspecified graph is not fundamentally related to the quality of the causal model, but the solution, for a couple of reasons, and the solution, the core idea, is to count the number of misspecified pairwise interventional distributions. So you look at a set of outcomes and treatments and ask, in how many cases do we have the path right, essentially. And so we can do that too. And in this case, again, the same graph. This has one causal quantity that would be misspecified. This has none, and this has 3. Okay, so structural intervention distance has a different set of errors here, and you might argue a better sense of that. But we still have no idea the effect that this would have in terms of the causal estimates for particular treatments and outcomes. So what's wrong with just using structural measures? Well, first of all, I'd say it's loosely coupled to what I think of as the well-specified task. Structural accuracy is neither sufficient nor necessary for high accuracy estimates of causal effects. It's not necessary because there can be edges that have essentially no effect or very small effects. And it's not sufficient because you could make very small errors on very important edges, and that could completely mess up your causal estimates, or you could do a bad job of parameter estimation. And also, just a side note, you can't really focus in on particular nodes that you expect to be the ones that you intervene on, and particular outcome variables that you expect to be the ones that you really care about. Structural intervention distance actually does do this, but structural Hamming distance typically does not. So going back here to the model that we talked about, there's a whole bunch of edges here, arguably roughly half the edges, that really are almost unimportant to the causal estimates, the distributional estimates we make, because they're just so weak. Okay? There's other edges, like edges over here, that don't matter if we're intervening on these variables and looking at the outcome on these variables. We do care that the model didn't stick any of these variables in the middle here. It did the right thing and kind of sidelined them. But ultimately, if we make errors among these variables, it doesn't much matter to the particular set of treatments and outcomes that we cared about. It also does something really insidious, focusing on structural measures. It limits how we could compare alternative representations besides, say, directed graphical models. So if somebody came up with some really great method for doing causal estimates that was not a DAG, we can't use a structural measure to compare directly these methods. We could use a distributional measure, because I would presume that this new model would estimate a causal distribution, but we're not able to just look at the structure and say, it's right or it's wrong. Ideally, we should have evaluation methods that are representation agnostic. It also prevents the use of empirical data sets. If I have a really interesting case out there, even when I can do massive numbers of experiments, I can't do structural measures because I don't know what the true model is. I'd have to somehow approximate the true model, and then I'd have the problem of, is it my approximation that's right, or is it the modeling method that's causing the problem? So we either need essentially an artificial generator in the form of a DAG, or we need to have extraordinary knowledge of the underlying dependencies in that real system, and it's very unlikely that we will. And it's also, frankly, pretty unlikely that it will be structured as a DAG. So I just think that I don't want to commit myself to a view that says the world is a DAG, and that my evaluation would have to account for that. So in this way, I think we are preventing ourselves from doing potentially really impressive applications like TD Gammon or the Atari 2600 simulator, because we can't use real data sets, or it's harder to use real data sets. We also just don't get surprised. And anytime you do science, you should be able to be surprised by your results. And I think we're limiting our potential. It's not there's no surprises about the real world. We can be surprised that our simulators end up producing errors in our methods, but we ought to be able to get surprised by the way that the system actually generates data. So What are our alternatives? Well, fortunately, there are some alternatives out there. People have been thinking about this for quite some time. So one option is to compare interventional distributions on synthetic data. Keep your synthetic data generator. Just don't use structural measures. Instead, use distributional measures like total variation, TV, which is what we suggest. You can use KL divergence. You can use any of a whole set of other ways of comparing interventional distributions. But compare distributions. That's one thing you can do. You can compare interventional distributions on synthetic data intended to represent real data. And multiple researchers have actually done this. Take a real data set, learn a Bayes net, use that as your data generator, which is better than just coming up with one de novo. I'm pretty impressed by that. There's also, by the way, a DARPA program that started up recently. I'm not involved with it, but basically what they're having is one team develop social science simulators and other teams applying causality methods trying to understand the causality in those simulators. So there's at least separation between the people that are creating simulators and the people that are creating the estimates. You can compare inferences in empirical cases with known causality. The cause-effects pairs challenge is a good example of this. And that can even be done with just the strictly structural measures. But I think you could also do a really interesting job asking about interventional distributions. You can compare interventional distributions on real data with limited sets of real-world interventions. So there's examples of this. Richard visited UMass recently and talked about this Arabidopsis. I don't know if am I spelling it right? I hope so. Okay. Very interesting data set that I hadn't known about. And there's the DREAM data, where this is molecular biology interventions. And there's a few other data sets where people have been able to do interventions and then test that out. And then you can use the observational data to build a model and make those estimates. You can do what we did in the paper I mentioned, where we compared interventional distributions on real data, where we're able to do nearly exhaustive experimental studies. And then finally, just wanted to mention something. So William Schottish has done some interesting work over the past, I think, 5 years, where he does these doubly randomized studies, where he takes a set of people and he says, half of you are going to be randomly assigned to the one arm and the second arm. The first arm, you do a randomized controlled trial. The second arm, you allow the subjects to choose their own treatment. And then you apply various methods intended to deal with that confounding. And then you compare the estimates at the other end. The results are not encouraging. Okay, sadly. But it's a really interesting attempt to do a very careful analysis of whether things like instrumental variables or interrupted time series or other methods work well. So just a couple, almost done now, a couple of things. So what should we do? Well, the first is I think we ought to be creating more alternative evaluation methods, developing new data sets similar to the ones I've talked about, the ones we've developed, DREAM, Arabidopsis, these data sets where we know something about where they're real systems, but we know something about the interventions. Those might be cyber-physical systems, those might be small-scale biological systems, and might even be just really good synthetic data generators, perhaps. And some more standardized, I'm not arguing completely standardized, but more standardized evaluation protocols. Should make these available in shared repositories, carefully curated, and we should be driving this into practice and telling people when we review papers, you should be doing better evaluation and here's where to go to be able to do that. But until it exists, we can't really push people that hard. If we do that, here's some things I think we're likely to get. We're likely to get wider recognition of the utility of the methods we have developed outside of our own community. Within our community, I think we'll get a clearer sense of comparative effectiveness of alternative methods. So one of the things I would really like to do is have very sensible things to say to people who come along with the potential outcome framework or quasi-experimental design and say, oh, those crazy people who do graphical models, I would like to be able to say, well, we did a head-to-head comparison of empirical data, and here's what we got. That might tell us some things, but it would tell the larger community some really interesting things. We also might find out that directed acyclic graphs may not be representing everything we care about. And we might need to come up with more mechanistic, more detailed causal models, and look at things like within subjects design. Happy to talk about that offline. In terms of comparing to distributional methods, there might be some interesting comparisons there. We might find out that certain key assumptions aren't really that important, or we might come up with new, unrecognized assumptions that are very important if we do this kind of work. We might get surprised by how the real world works, and be able to develop methods that unify multiple traditions and do a better job in combination. So, just to refresh what I said earlier, our understanding of both methods for causal inference and practical techniques could substantially improve if we were to use empirical evaluation, more empirical evaluation, broader and more consistent use of those methods, and that I think that we would get, well, better quality, better external impact. And that's it. And if we still have a little time, I don't know how much people have to run off, but I'd be happy to answer questions and talk offline.
Is there a reason that you can't use DAGs on recurrent neural networks?
What does it mean to use a DAG on a
let's say
deep network?
You have a deep network that works.
Yep.
You want to now apply your technique to there's efficiencies or a metric of performance, and then you reinitialize the network and let it learn again.
Yes, and it is exactly what we've been doing in my lab for about the last 4 months. We've been working on trying to use causal graphical models to explain deep networks, and it's been tough going, but we've gotten some very interesting results. I will be talking about those at CMU on Monday, if you're interested in hearing about explainability and causal graphical models. So. Wow, I actually don't even know the time, okay, sadly. The Heinz School is who invited me in, but I don't know what time they have me scheduled, unfortunately. I can send it out. Okay, that'd be great. Thanks. Peter.
Feasible then your data. I could sort of add things in one by one. That sort of like.
No, it doesn't take 1,000 people. It takes a small number of relatively smart, computer science graduate students who know how to hack systems. Dan was amazing. Okay, he just knows how to make systems work, and so he was able to install a whole bunch of software and get it all running and do a whole bunch of these experiments. It turned out to be much more complicated than you might imagine, but still doable. And I actually think that that's the direction to go. That we should be extending and adding new systems, but extending the kinds of work that we do with those systems to introduce as many of the complexities as we think are reasonable, and then making those available both in the terms of here's a bunch of data, you don't even have to know how to install this stuff and get it to run, but also, by the way, here's how to reproduce it. If you want to go gather new data on your systems, here's the version numbers we used and all that kind of stuff.
And the original data is there so that your observational data, it's easy to vary what makes observation.
Yes. We provide the exhaustive experimental data where we did 5 trials under all possible combinations of treatment configurations. Yep. And this is absolutely extendable, and I'm very interested in doing that and already talking with a few people about it. But seriously, if you are interested in this, contact me. I'm putting together a cabal, okay, to do this so that we can get and what I would hope is that we can get resources out there and we can get a few like survey papers out there with authors, a large number of authors from around the community to say, look, this is where we think the community ought to be heading. If you agree with me, if you don't agree with me, please come argue with me, and I would like to be disabused of things that I'm incorrect about, or try to disabuse you of your mistaken views if that is what turns out to be the issue. Correct.
One of the things that was intriguing, and I was why you did, which is Atari 2600 environment and similar game kind of setup. It's a little bit more intuitive, expressed by. So if you're trying to sort of express the outer world rather than sort of databases and operating systems, you're able to reproduce all the discovery in the Atari 2600. What deep learning, or deep mind, is able to do there. I guess it's that.
So I will call your bet and I will raise you. So yes, Atari 2600 is great. We just weren't doing it until relatively recently, and I agree with you now that I've spent some time with it. And the raise is that there are much more interesting simulators out there, such as StarCraft. Okay, StarCraft is, in some ways, it feels very realistic, but it is totally resettable in the sense that you can. It turns out the Atari 2600 simulator, we don't have as much control over it as you might think. But StarCraft really does. Yeah.
Environments that you can get in and you have the system observe what's going on as well as intervene.
You're absolutely right, and you can reset. You can go back to it, sit and say, what if you intervened differently?
So have you started using some of those?
We have started certainly building causal models on deep networks that play Atari games. And so actually at this point, what we're building is a model of how the deep network plays the game rather than a model of the game, which is a subtle but very interesting difference, and a perfectly viable target for causal modeling. But we could also be asking, how does the simulator work? We have bounced around ideas of trying to learn the rules of certain kinds of games, like baseball or soccer, okay? But probably where we're going to head next is keep doing Atari, but also go to the StarCraft simulator. There's also some very interesting driving simulators that have been designed to be really high quality. And you can intervene in all sorts of interesting ways in the driving simulator. What if the road conditions had been, what if there had been snow? What if it had been nighttime? What if there had been pedestrians? All of those things. And that's, again, a very realistic situation where you care about how well that autonomous vehicle drives. Yeah, great suggestions.
So in your model, you eliminated sort of the weak edges.
I will say we eliminated them for exposition, but they were actually in the model for all the estimates.
So the different design where you have any more weak value logic of eliminating.
So I will just point out I eliminated them for display here, but when we made our estimates, they were in the model and active. They just didn't have much of an effect because they're weak. So
I guess what I'm saying is, if you had a different design where you had many weak connections, where you could get emergent properties, how that would change your.
I mean, I think it would be interesting to see how different algorithms deal with that situation. First of all, because really dense networks, my experience has been, can be a real problem for these methods, because if you get a weird cascade, particularly for things like PC, although stable PC and some other methods can deal with it, robust PC, but if you get these sort of cascade effects of edge orientation and other things that happen, and also if there's really a lot of weak edges, so much so that you would leave some out by having some kind of alpha set too high too low, in your hypothesis tests. It's a very interesting question to ask. Kind of, I don't know how alternative methods would work, but I would argue that distributional methods of evaluation are still likely to be what you should be doing, rather than purely structural measures. Yeah.
Just one kind of comment. Sometimes when you use a causal search algorithm, what you want to know is the causal structure. You want to estimate the causal structure. in which case the edge estimates really are perhaps helpful.
So tell me the scenario
Well, I mean,
under which you really care about the structure and don't care about the causal estimates. I'm still trying to figure that one out.
also like who is doing these cancer estimates? So he's trying to find causal pathways so you can figure out which variables to intervene on to eliminate cancer.
And you don't care at all about the strength of effect?
Oh, I do.
Okay.
I do, but I'm just saying that the edge estimates may be helpful if you want to know what the causal structure is.
Well, I'll give you an example. Maybe it's a little bit. In hazard identification, environmental toxicology or toxichemical, there's essentially 90,000 chemicals that are involved in the industry or in the environment. And for each one of those chemicals, there's about 10 or 15 different health outcomes you might care about.
Okay.
Neurotoxic effects, developmental effects, different cancer, different kinds of cancer, et cetera, et cetera, et cetera. So before you actually go to the effort to do estimation at some more fine-grained level for what the size of an effect is, you need to know which things are hazard. And then...
Don't you want to have a ranked list, though, of priorities rather than just a yes-no?
You don't have the data. I'm saying it's sort of there's an investment you have to make in data collection to get you something much more fine-grained.
But you do have the data necessary to actually determine whether the edge is there.
Partially, yeah. And it's, in some cases, it's a molecular model, saying whether there's going to be a particular pathway that's going to be affected. And then you don't know. Suppose you find out the molecular model says, yes, this pathway is going to be affected by this chemical. I don't know whether it's going to be affected strongly enough or how important that pathway is to getting to health outcomes. But then you need to get more data, this dose response level, to figure out the size of the effect.
Aren't you really saying the edges are just too weak? I'm going to ignore.
No, you are. I agree. I agree totally. But in the end, what you're looking for is strength. So if there's an edge there, but it turns out it's too weak, okay, we're not going to care. But what I'm saying is, you don't have data in the initial stages, in some cases, to even tell you there's a quantitative size of an effect. You just have a qualitative model that says, yes, there might be a pathway.
So is this a learned model from data, or is this a model from, like, prior knowledge about?
In the toxic chemical cases, it might be a model from the molecular structure of the chemical.
Right.
Right. And then you can't have any idea of the size of the effect until you gather it, either on animals or humans. Okay. So on the animals, right, you might have an effect, know the dose response and the size, but you don't know the size of it's going to be what it's going to be in human. You just know that there will be one. Then you actually have to also get data on humans to figure out the size of the effect. So it's completely compatible with your end goals. You need to know the strength of the effect, and if it's a weak edge, you don't care.
Yeah.
But there is clearly a need to do what they're calling hazard identification to actually screen out which of the things you want to get quantitative information about.
I mean, believe me, I still think figuring out edges is important because it is not sufficient, and it is not perfection is not necessary. But you want to do a good job of it. But I really think it's almost always, there are edge cases, but it's almost always in the service of eventually getting ourselves to an interventional estimate.
I totally agree.
Okay.
We're on the same page.
Yeah. I mean,
You challenge us to find any context.
Okay. We have just gotten pushback in review comments, which have just blown my mind. Where people say the really important thing is just figuring out whether the edge is there. I don't know why you're talking about distributional estimates.
You've been doing this for a lot of years. Watching stupid reviews.
I just didn't expect that one. Okay, I expect maybe some other ones, but and we got them. But and the paper could be better written. There's lots of things that we could do better. There's no question. But still, I was surprised at some of the responses we got, and so that's why we're trying to better formulate the issue. Love to go on talking, but we should probably let people go. Thank you very much.